So here we go. Bonding. Okay. We're talking about bonding. They're using bond in the meaning of stick together. Okay? Bonding means sticking together. Okay? And what's responsible for them sticking together would be the electrons. Everybody okay with that? Hey, so we need to keep track of electrons, and we've shortened electron configurations so we can see what the valence electrons in those pieces are. But even that's more than a chemist wants to write every day. Okay, so there's another way to keep track of those electrons. Okay, so today we're going to learn a new way to keep track of electrons that will focus on the electrons we want to focus on and talk about how those electrons are moving around. So, which electrons do we really need to keep track of? The valence electrons, the outer energy levels, the valence electrons. Those are the ones I need to keep track of. Hey, I need to keep track of the valence electrons. The ones in the outer energy level, the S's and the P's. Now, as you're copying away, think to yourself, do I need to copy this, or can I just look at it the last time I wrote down these sentences? Right? It's the valence electrons that do everything. Okay? And we need to be able to find the number of valence electrons. We could write out the whole electron configuration, but remember there was an easier way. Okay? Atoms in the same column have the same properties because they have the same electron configuration, which means they have the same valence electrons. Right? That was one of the big ideas we got to last chapter. The outside electrons do everything, right? So if you got this, so when I approach an atom, I care what it looks like on the outside. Okay. And to find those valence electrons, we can write the electron configuration and add up the S's and the P's, or we can just look at the group number. Okay. So group 2A, calcium, would have 2 valence electrons. Everybody with me on how to get valence electrons fast and easy? Okay. So valence electrons are the key to bonding. So let's keep track of them. To keep track of them now, we're going to use something called an electron dot diagram. Occasionally, you will hear it called, instead of electron, they will call it a Lewis dot diagram, because a guy named Gilbert Lewis figured out how to do this. Some of you may have done this one before. I may give you a little different view of it. And all it is a way of keeping track of valence electrons, because those are the ones I have to pay attention to. So the first step in using electron dot diagrams is being able to draw them. So here's how you draw them. First, you write the symbol. I have put in a big capital X where the symbol will go. There is no element X. There's an XR, but there's no X. No, XE, sorry, XE, but no X. Okay. And then you put 1 dot for each valence electron. Now you will notice that I have put a total of 8 dots there. Okay. Why 8? S's, 2, P's, 6, noble gas configuration, right? Double gases are going to have 8. Okay. The question is, if it doesn't have 8, where do you draw the dots? What order do I draw these dots? Well, here's the whole answer. They don't pair up until they have to. That's the whole answer. Your other teachers may have said a specific direction because they wanted to look specific. No, we need to be able to move those dots around. We just need to follow the rule. They don't pair up until they have to. Okay? So if I put one dot on it, I can put that one dot on either side. So we don't want to think of this as 8 electrons. We want to think of this as 4 pair of electrons. A top, a bottom, a left, a right. Okay? So don't think of it as 8 electrons, think of it as 4 pair, and they don't pair up until they have to. Okay? So let's show you how it's done. Let's draw the electron dot diagram for nitrogen. Okay, I look up nitrogen on the periodic table for 2 reasons. One, to make sure what the symbol is, it's N, and the other to say it's in group 5A. So it's got 5 electrons, and I can write a capital N. Okay, write the symbol. I've noticed a few of you got to be careful when you're writing symbols. First letter capitalized, second letter lowercase. Then I put on the dots. Where do they go? It really doesn't matter. First one can go on any side. The second one can go on any side except next to the first one. The third one goes on one of the 2 empty sides. The fourth one goes on the other side. And now I go to the 5th one, it's got to pair up. Where do I pair it up? It doesn't matter. Pick any side. Okay. I went clockwise that way. You don't have to. Okay. I understand why your teacher in the past would ask you to do that because it makes it easier to grade, but it makes it harder to do chemistry. Okay. Because I need to be able to move those dots from side to side. So let's try a few. Write the electron dot diagram for Na. Was that the only possibility? No. There are 3 other possibilities. Right? I can put that dot on any side. When you're making dots, make sure I can see them. Don't just tap your pencil to the paper. Remember, I'm horrible at guessing. If I have to guess whether it's a dot or not, I always guess wrong. Okay? So what about Mg? Okay, so Mg is in group 2A. Got to put on 2 dots. There's only one wrong way to put on those 2 dots, and that's to put them together. You do this, that's okay. It's probably not the one you chose. People tend not to choose the bottom and the left, but that's what I chose. They could be on both sides. It doesn't matter where they're at. This is not saying where the electrons are. It's just counting them. Okay? It's just counting how many there are. It's just a way of counting. Let's see if we can do another one. This one's a little trickier. There's only one right way to do this one. Because it's group number 4, right? It's 4, so I got to put in 4 dots. The first dot can go anywhere. Second dot can go anywhere. Third dot, one of the empty sides. The fourth dot, got to have one on each side. Oh, that was easy. So O is in group 6A. So 1, 2, 3, 4, 5, 6. 6 dots, 2 pairs, 2 unpaired. Let's see if you can do this. Okay, it's in group 7A. So 1, 2, 3, 4, 5, 6, 7. 3 pairs, 1 unpaired. Let's see if this works for any element. And of course, NE is in group 8A, so I draw 8 dots. And there's only one way to draw 8 dots, and that's 4 pair. Okay, there are exceptions. The only exception, actually there's an exception. There's only one exception. See if you can figure out what the electron dot diagram for helium would look like. Okay, so the first thing people catch pretty easy. It's in group 8A, but you do not draw 8 dots. It only has 2 electrons. Okay, but here's the trick part. They're paired. You pair those because it's full. It's stable. Okay, so I pair those up because it really has all it can hold in the first energy level. Okay. So helium's an exception for 2 reasons. One is it's 2, not 8, and the other is you pair them up because that lets somebody know, looking at it, say, oh, it's full. I'm not going to mess with this atom. Okay, it's not going to change. So, which is the correct electron diagram for sulfur? Okay, it's in group 6A, 6 electrons. So these two both have 6 electrons. It's B, because they don't pair until they have to. Look at that. Pretty simple set of rules, right? So when I ask you to draw electron dot diagrams today, you're okay. Okay, so here's what we use them for. Metals are always going to have very few valence electrons. Why? They're on the left-hand side of the periodic table. Okay, but why? They have low nuclear charge on that period. The why is about the low nuclear charge, but metals are on the left end. Left ends have low numbers of valence electrons. Okay? How do metals react? They form cations. And how do you form a cation? Losing electrons. How many electrons do they lose? They lose all of their valence electrons. Those valence electrons come off. And when they come off, see how this is showing that we emptied the energy level for calcium. This is about that test question. This shows that you're emptying that energy level. Okay? And what do you get when you take off electrons? A positive charge, noble gas configuration. But this is not a noble gas. It won't behave like a noble gas. It'll look like a noble gas, but it won't behave like one. Because since most of our bone, the calcium in our bones is calcium 2+, it's not acting like a noble gas because it made something. Okay? That's how you make cations. Electrons come flying off. And which electrons come off? All the valence electrons. Now this only works again for S's and P's, representative elements. The D's we're going to have to treat differently because the D's all have, most of them have 2 valence electrons. because it's 4s2, then 3d10. So 4s2 is still there. Just at our exceptions, they have 1. 4s1, 3d5.
We'll see what happens when radioactive elements form compounds.
They behave just, you now have radioactive compounds. Yep, once it decays, that compound probably won't stay together. And that's why they have to worry in nuclear power plants is the radiation hits the steel, changes the iron into something else. So your steel disintegrates over time. Because if it's not iron, you don't have steel. So your building falls apart because the atoms that make it up change. That's a bad thing. Okay. Let's do the other way. What about anions? Yeah. They gain electrons. And we don't need to talk about the electron configuration. They're going to get noble gas configuration. We want to talk about dots, right? Non-metals will have lots of valence electrons. Why? Well, over on the right-hand side, they have a big nuclear charge so they can hang on to lots of charge. There. So how do nonmetals react? Metals lost their valence electrons, and nonmetals gain. How do they gain? They gain enough to fill it up. They gain enough to achieve noble gas electron configuration. So how many would it take to fill up phosphorus? 1, 2, 3. It took 3 electrons to fill up phosphorus. So it's going to make an ion with a 3- charge, which we would have predicted from electron configurations yesterday on the test, right? Phosphorus is here. It looks like a noble gas. It'd have to gain 3 electrons. So see, the dots are just another way. Whoa, I stepped on something. The dots are just another way of showing electrons. Okay? It's a lot shorter than writing electron configurations. Easier to manipulate. I mean, when you did the reading in the book, when they were working with those electron configurations and lining up those orbitals, it was hard to see what was going on, right? Okay? So we'll see today the big advantage of using dots to do it. It's just an easier way to explain it. So, show how the following form ions. How would aluminum form an ion? Aluminum is in group 3A. So it gets 3 dots. What happens to those electrons? They lose, they go away. So I end up with an aluminum without dots, that is 3 plus, and I have 3 electrons that are left over. Make sense? Okay. What about Cl? Chlorine, it's a halogen, so it gets 7 dots. How could it look like a noble gas? So I'm going to put plus an electron on this side. I have to add the electron in. Makes a Cl minus that's completely full. but carbon. Okay, carbon's in group 4A. I draw my 4 dots. You could lose 4 or gain 4. Which one's it going to do? Well, is it a metal or a non-metal? It's a non-metal, and non-metals are gainers. So I'm going to have to put in 1, 2, 3, 4 electrons to make my carbon full with a 4 minus charge. Yeah.
So when we're showing that we're gaining, do you recommend like drawing dots and arrows?
Draw the dot. So I got the arrows are showing what's happening with the electrons, either coming in or going out. So you have an arrow going into a hole, because I look at it, it's not just as four dots. I see it as 4 holes too. Yeah. They can do either. Depends on what you put them with. Oh, we got to talk about this. We're still talking about it by ourselves, and our goal is to stick them together. We're going to make them stick together.
So when certain elements are losing their electrons, where are the electrons?
Going. No, let me ask you another question. When nonmetals gain electrons, where are they coming from?
The metals that are losing electrons.
From the metals that lose them. And that's a chemical reaction.
So they're just going back and forth.
And that's a chemical reaction.
Show covalent bonds through.
Yeah. We're going to do covalent, but we're doing ionic bonds first, and then we'll get to covalent bonds. Okay. Okay. Stable electron configurations. That means they store them in a barn. No, that's horses. Stable, unlikely to change. Stable electron configurations, noble gas electron configurations. Noble gases have 8 valence electrons. So they call this the octet rule. The octet rule says that atoms react to achieve noble gas electron configuration. The octet rule is not that they get 8 valence electrons. You might think that would be it. But there's a way to look like a noble gas and not have 8 valence electrons. Look like helium. Helium looks like a noble gas, and it doesn't have 8 valence electrons. Okay? So the octet rule is not 8 valence electrons. Usually it's 8 valence electrons, but that's not the rule. The rule is look like a noble gas. And now we can make sense to call it the octet rule. We can draw pictures like that. And we refer to those four pairs of electrons around argon as a stable octet. Okay. Well, so we've limited ourselves to representative elements for a while. I do need to talk about transition metals. We won't do it with dots, but we talk about the configurations. Okay. Transition metals are metals. They form cations. But the reason why we don't label them with how many they lose or gain is because it's hard to predict the charge, and most of them make more than one charge. Sometimes iron loses 2 electrons, sometimes iron loses 3. Chromium can lose 2 electrons, 3 electrons, 4 electrons, or 6 electrons. Okay. And end up stable. Okay, do you think that copper is going to lose 11 electrons and look like argon? It would have to lose 11 electrons to look like argon. Okay? It's not going to lose 11 electrons, is it? No, but how about this? How about iodine losing 17? Not going to lose 17 electrons. That's not going to happen. Okay? Mercury losing 26 electrons. Not going to happen. They can't form noble gas configuration. They're not going to lose that many electrons because it takes way too much energy to knock off that. Remember, the energy goes up every time. So by the time you're knocking off 10 or 11, the numbers get pretty big. And no chemistry is going to make that happen. But they want to fill orbitals because full and half full are more stable. So they make something called pseudo-noble gas electron configuration. Pseudo, the prefix pseudo means similar to or like. It's got a connotation of fake, but it really just means artificial. It's almost like an analogy. This is like a noble gas. And it's like a noble gas in that it has full orbitals. Because that's why noble gases are stable, is because all their orbitals are full. Yeah. Again, pseudo means similar to or like. Although other places it normally has a negative connotation. Good news. I am not going to ask you to predict what charges the transition metals do. What I am going to ask you to do, though, is I'll tell you the charge, and you tell me why it formed. How do you end up with full orbitals with that charge? So, for example, zinc. To write the electron configuration of zinc, it is 3d10 at the end. Normally we'd write it as argon 4s2 3d10. When zinc reacts, it makes a 2+ ion. How can how can electron configuration explain why zinc makes a 2+ ion?
Because it has two bonds.
Yeah, so it loses that 4s2. If you lose the 4s2, you have a full third energy level.
So it can't be stable.
No. It's as stable. It's as stable as any other ion. It's got a configuration that's completely full, and that's hard to change.
Is it as stable as a noble gas?
It's hard to say because it's going to react because of the charge. Okay, because noble gases have that arrangement without a charge, so they're going to interact with less atoms. Okay, but zinc is going to have a 2+ charge, so anything negative nearby, it's going to draw in. And so it's going to be hard to tell what it was doing because of the charge. Okay. Right. Iron, we would write argon 4s2 3d6. Iron makes a 2+ ion. How could you do that? If I take 4s2 off, that won't work this time, will it? Because that leaves 3d6.
Oh,
Take 1s and 1d, and I end up with half-filled. Okay? Oh, ideas we learned before are coming back. Get to filled and half-filled is stable. Okay? Iron sometimes forms a 3+ ion. How would it make a 3 plus ion? You take both 4 S's and one of the D's. Okay? So see what I mean by you have to predict how they could be stable. I'm not going to ask you to predict this piece of it. Okay? Because you don't know what it's going to do. Okay. So that's how the individual atoms behave. Now we're going to put them together. And the first type of bonding we're going to talk about is called ionic bonding. So sodium is in group 1A. It gets 1 dot. Chlorine is in group 7A. It gets 7 dots. How is sodium going to change? It's going to lose 1 electron. How is chlorine going to change? It's going to gain 1 electron. So we're talking about the same electron. The electron from sodium moves to chlorine. When it does that, now the sodium has a positive charge and the chlorine has a negative charge. And they stick together. And that's how you make salt. You would not want to put sodium in your mouth. You saw what happened when you put calcium in water. Think about what an alkali metal is going to do in water. I didn't give you one of those. It would make a big bubble of hydrogen, light it on fire, blow your mouth out while it was turning it to drain out. Okay, that's a bad thing. Okay, chlorine is one of the gas they used in World War II. It was in World War I when they poisoned the trenches. They sprayed chlorine gas. Chlorine's a nasty chemical. It's a yellowish green gas. Do either of those sound like sodium chloride? No, because sodium's really active. It wants to get rid of its electron. Chlorine's really active. It wants 1 more electron. When they do this, they're stable. They don't need to change very much. And it's okay for us to eat it.
Is that why halogens are called salt formers?
That's why they're called salt formers. That's where the salt former came in. I know I tell you that in the beginning, but it doesn't make sense until you get here. Right here, now it makes sense that they're making salts. You've been salted. Oh, that worked out real nice because sodium wanted to lose 1 and chlorine wanted to gain 1. What if I put together calcium and phosphorus? Calcium has 2 dots because it's in group 2A, an alkaline earth metal. Phosphorus in group 5A gets 5 dots. And here's the key. Every electron has to be accounted for, and everybody has to end up happy. So I got to empty all my metals and fill all my nonmetals. So calcium gives 2 of its electrons to phosphorus. That makes the calcium happy. It looks like a noble gas with a 2 plus charge. The phosphorus is not happy. It needs another electron. Where could it get another electron from? The answer is another calcium. Are we ever going to have just 1 calcium atom? We're going to have a pile of calcium, aren't we? So there'll be lots of calcium atoms laying next to this. It takes an electron from a different calcium. That makes that phosphorus happy. But that calcium's not happy. It's got an electron to give away. Where could it give it to? Another phosphorus. This just happens, yeah. You want to stand back, it's going to be pretty explosive. You saw what calcium did with water. And water's pretty stable. Phosphorus is not what I would call stable. Okay. And that makes the second calcium happy, but the second phosphorus is not happy. It needs electrons. Where can it get electrons from? Another calcium. It's going to work out eventually. Okay? They'll always work out eventually. You just don't know where they're going to work out until you do them all. So it gives those 2 electrons to that phosphorus. Okay? That in order for this to work, it takes 3 calciums for every 2 phosphoruses. Okay? So we can say that we will make Ca3P2. Oh, I don't know if you noticed this, but what we just did was we started off, I told you which 2 pieces you put together, calcium and phosphorus, and you figured out what they were going to make. Ca3P2. So how would Mg and Cl form an ionic compound? Calcium phosphide. I don't know what it's used for. We'll learn how to, our next unit is how to name all these things. That we're drawing them and building them, and then we'll learn how to name them. So Mg, 2 dots. Cl, 7 dots. Mg gives an electron to Cl. But then that Cl is full. So I'm going to need another Cl to take that other electron. So when I'm done, I end up with Mg with a 2 plus and 2 Cl's with a minus charge. So it's Mg, Cl2.
How do we know the order?
Metals first. Metals always first. Positive piece always first. No, they had to make a decision because we didn't want 2 formulas for everything. So they said, we'll put the metal part first, the positive piece first. We'd have 2 metals. 2 metals don't react. No, they don't ever react. Oh, no, they don't react with each other.
So why not? How come in the formula Mg doesn't have it too?
Okay, because here, this whole thing is neutral. Oh, no, Mg doesn't have a 2 because it's that 2 is a charge, right? And those charges cancel each other out. 2 plus, 1 minus, 1 minus. Right? Chlorines to make it equal 0. It's because compounds don't have a charge. Okay? So your homework's going to ask you to read about drawing electron dot diagrams. Okay? And what we can do with those. And then you're going to draw some electron diagrams. Do all of those on the same page. Don't kill 2 trees. Okay? I'm going to grade it as 1 assignment. So don't kill 2 trees. Right? Have a pleasant afternoon.